Hello everyone, welcome to another episode of GPU programming with Mojo. Today we look into vector addition and see how it's implemented on a CPU and compare that to how it's implemented on a GPU using Mojo. Vector addition is a simple operation where you add two vectors element wise. You take the first element from vector A and add to the first element in vector B and then store it in an output vector. So in this case 1 plus 1 becomes 2, 2 plus 2 becomes 4, 3 plus 3 becomes 6. Using a CPU, you would simply write a for loop where you would loop through the elements, the size of the elements, and add the elements from A to the elements in B. The inherent the inherent problem is as the data grows, the time required to process this loop also increases. Suppose you have 100 elements, it takes you 100 times. If you have a million elements, it will take you that much longer. So in computer science, the time complexity for such an operation is defined as big O of n, which in layman terms essentially means more data equals more time. Now let's see how we can design it for GPU. So we start off thinking about threads. Threads are the smallest unit of compute. If we can somehow ask each thread to execute one operation, and that one operation being that each thread can take one element in a vector from both the vectors and add them up. So for example, we say thread 0 can access A of 0 and add them to B of 0 and store them in result of 0. We ask thread 1 to do the exact same operation but access the A of 1 and add them to B of 1 and store it in result of 1, and so on and so forth. So if we can instruct all the threads to only access a certain element in A and a corresponding element in B and store it in result, then all of these threads, as we know on a GPU, execute in parallel. Essentially, all these 100 operations here that you see on the screen are executed at the exact same time. So whether you have 10 or 100 or million, since all of them happen at the same time, the problem that we had with the CPU version where time increases with data does not apply here. So in computer science, such an operation is called big O of 1, which means regardless of the data, pretty much the time remains the same. And that's the power of GPU. GPU kind of can help with these kind of operations where they are simple, but they can execute all of them in parallel. And this is referred to as single instruction multiple threads model. And it's one of the fundamental designs in GPU programming. Now, as we know in the first video of the series that threads are arranged in blocks and they have what's called as a thread ID. So a typical 4x4 layout looks like this. You have thread ID ranging from 0 to 3, but in block 0. The same 0 to 3 repeats in block 1, and so on. But if the thread IDs are repeating within each block, but our design says thread 99, thread 100, thread 89, and so on, then what we need to do is we somehow need to take this local thread ID within each block and translate them into what's called as a global thread ID in the form of 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Only then can we take advantage of this design. Or else if it is just 0 to 3, 0 to 3, then this algorithm or this design cannot be achieved. Fortunately for us, it is easy to derive the global thread ID from the local thread ID using this formula. So when we take the block ID multiplied by threads per block and add the thread ID within each block, we get as a global thread ID. So let's take an example. So suppose we are referring to block 2 thread 0, which is block 2 thread 0, which a global identifier for such a thread would be something like 2, which is the block ID, multiply by 4, which is the threads per block, plus 0, which is 8. Again, if you arrange it in a matrix format like this, you can read it yourself and arrive at the answer quickly. So this is 0 to 4, 0 to 3, this is 4 to 7. Naturally, this becomes 8. And even if you use the formula, you arrive at the answer 8. So by using this fundamental global thread ID derivation, we can go back and implement this design, which helps us solve the problem of executing such operations on a GPU. So now that we have designed the algorithm, we have derived what's called as a global ID. So we have all the elements in place. So we have to translate our pseudocode or design into a Mojo code. We start off like all the videos in the past by importing libraries. We initialize certain data types, layout style, and we pick 9 elements for this example. We pick block size of 3, and then we get the number of blocks, which obviously is 9 divided by 3 is 3. So we have 3 blocks and 3 threads which in each block. So the total number of threads we are going to create is 9. And we have tactically made sure that we create a vector of 9 elements. So 9 threads, 9 elements. We start off writing a simple function, which in the GPU world is called a kernel. We take the LHS tensor, RHS tensor, and the output tensor. Essentially, this is the A vector, the B vector, and the result vector. We apply the exact same formula which we discussed about to get the global ID. Then we say A of global ID plus B of global ID thread gives and store it in the result vector. See how it's simple that the exact pseudocode that we derived is translated into code. So the code is as readable as the pseudocode. And that's one of the hallmarks of Mojo. It is highly readable. It looks Pythonic, but it runs as fast as C or C++. And the same program that I'm showing you here runs, which is now running on my NVIDIA GPU, can also run on AMD and on your Apple GPU. So it's like the best of both worlds, where you can run it on any hardware and still have a readable code under your supervision. We start off getting a reference to GPU using device context. We create a buffer, which is allocating memory for the 2 vectors that we are going to initialize. We use a special map to host to initialize the A vector with 0 to 8. We then initialize the B vector with again 0 to 8. We verify whether they are being initialized correctly. It looks like the A vector has 9 elements ranging from 0 to 8. We see that the RHS or the B vector also has 0 to 8. Then we create the result vector. We need a vector to store the result, and that's what the result device buffer represents. As in the last video, we take the buffer, which is the memory allocation, and we wrap it with what's called as a layout tensor. The layout tensor is an abstraction which kind of helps you do some complex and safe memory operations that you will be doing in many complex GPU algorithms. But instead of you tinkering with the device buffer and arranging it in a row major or a column major, the layout tensor gives you a nice abstraction that you can tap into. Finally, once you wrap them in layout tensor, you pass them to the queue function, which calls the kernel that you just wrote, which is vector addition kernel. Finally, you print the results using the map to host again, and you see that the result device buffer, which holds the the result of a of I plus b of I that we executed on a GPU, and we see that the results have added up to 0, 2, 4, 6, 8, and so on, which is nothing but the addition of two vectors. Now, most of this code is pretty much boilerplate that you have to write to ensure that you execute a program on a GPU. But the key thing to remember is that the kernel that you wrote is the main design or algorithm that is running the operation, and you first ended up designing it above, and then you translated your pseudocode into Mojo code, and it turned out to be just 2 lines of code which executed the vector addition. And remember, you can have 1,000 elements and all of them would execute in parallel using 1,000 threads. And that is the power of GPU operations over a CPU. Hope you enjoyed and learned something about vector addition and how we can convert a seemingly simple CPU operation into a parallel processing GPU operation. We will look into more such algorithms in a further video series. Hope you liked it. Stay tuned. Thank you.